Okay, so I've emailed all of you and asked if you're still interested in doing an extra credit presentation. I haven't put a lot of emphasis on this yet because I knew this would happen. We have, hey guys, shut up. I knew this would happen. We have a number of people who have grades that might make them think, well, I'm doing okay in this class. I'm going to put some time into biochem, and I don't want to spend the time on an extra credit project that can't lower my grade because I'm happy with my grade. So please let me know if you're interested in doing that project. Only a couple of you actually really probably should do it, like to ensure that you pass. I mean, really, 41 out of 43 people in this class are passing at the moment, and it seems very likely that that will hold up. The two that are maybe below where they need to be can, I think, easily rectify that by taking the fourth exam and doing well, and maybe taking the final and doing acceptably. So I don't think that anybody has to do this project. And I've been doing this a long time. Nothing you say can possibly make me take this personally. If you don't want to do it, if you think that you have better things to do with your time, then get involved in a PowerPoint presentation on some topic, then I completely understand. It's okay. But do me the courtesy and do courtesy to the other people who might be expecting that you would do something toward that project to let me know so that we can make arrangements. If we're down to 2 people in a project and they haven't started anything yet, which I know has happened, and they still want to do it, well, maybe I'll pair them with another group that's lost a person or something like that. So please do email me and say yes or no, I want to do this project. Okay, because I will still honor it. You know, it's kind of an ad hoc thing. Like, you guys are expressing a lot of anxiety. Here's a way to maybe empower you. But it was a very ad hoc thought. So I know that some of you have already started working on this. Some of you have not. That's okay, because here's how we're going to think about it. Basically, I want you to think about it in terms of 5 things. What is the basic problem? How is it understood or reported in the press? Is it accurately understood, or do people misunderstand what's going on? What is the source of that problem? Are there things that you can do as an individual that will help address that problem in a substantial way? And finally, how might we need to rethink the way that we have organized society and established regulations at the governmental level rather than the individual level? And you can think of it basically as a 5-slide presentation. Take 1 minute per slide. That would be terrific. That would actually be really good. And just getting you guys to think about these issues in those terms, I think, is the main thing that I'd like to see. So, think about it that way. Think about basically kind of 5 slides-ish, basically 5 questions. And if you can put together a little presentation in the next couple of weeks on that, then I think we'll give you the credit. Now, I'm not going to give you credit if you're part of a group that's been working and you haven't done a thing. I'm going to ask your other group members, does this person do anything? And so I want some verification that you actually participated in some way. All right. If you've been having some issues trying to communicate because Moodle doesn't work the way I thought it did, I just emailed everybody in their groups, and you can reply all to that email. Well, you can take me off if you want, but you can reply all and communicate that way, okay? So does anybody have any questions about that?
What were the first two questions out of the five that you just said?
Okay, so what is the basic problem, and how is that problem understood or reported? Is it reported accurately? Do people have an accurate understanding of what the problem really is? Okay, and then what's the source? Are there things you can do on an individual level, or are there things that need to be done at a societal level? So there you go. Okay. And remember, the last thing I'll say about this is that some of these questions are like really big and open-ended. I don't want you to do that. I want you to get something, if you're going to do this, get something that's manageable. Like if you want to do a project on pollinators, well, maybe don't look at the worldwide pollinator problem in detail. Maybe just look at, like, you know, honeybees in the southeast or something. I don't know. That would be acceptable. If you want to look at marine resources, maybe don't look at the entire extinction crisis around the world. Maybe break off a little piece and talk about how coral reefs have changed in the last 30 years and what we might do to address that. So don't make it too big. Make it manageable if you're going to do this, okay? Any other questions? Okay. So we had gotten almost all the way through succession last time, and here we go. We made the point that we think of succession as a series of stages, right? You have early successional stages, middle successional stages, late successional stages, and then there's this community that we call the climax community that replaces itself. And people had, in the 20th century, at least early in the 20th century, analogized that to the growth and maturity of an organism. And they would actually say, oh, well, this is a young ecosystem. This is a young stage. It's not mature. And of course, we realize now, with having looked at many more systems, that that's not probably the way to look at this, because really succession can be circular here, and it's not easy to say what the climax community here would be. I mean, you could make the case for sand to be the climax community in this particular successional sequence, which of course is kind of nonsense. But that just is another consideration when we try to apply ecological principles that we think of as being good analogies that maybe kind of break down when you look at them closely. So we still talk about climax communities, but we don't take them nearly as seriously as we used to. So the last thing that we're going to talk about in succession is the different mechanisms that operate. And there are three different mechanisms that we recognize. They operate in different situations. So first, let's just list them. First is facilitation. In facilitation, each species in a successional sequence facilitates the colonization of other species. Each species changes the environment in ways that make it easier for later successional species to arrive and to stay. Now, this really kind of sounds like mutualism, like somebody's making a sacrifice so that other species can prosper. But that ain't the way it is, not at all. the species that are changing the environment cannot help that they're changing the environment, and they do not deliberately do that. They don't deliberately change the environment in a way that enables another species to come in and replace them. That is an accident of their living there. You typically find that succession proceeds as available niches change over time. This is the primary mechanism that we see in primary succession, where there has not been a plant community there before, when it's new land, say. Okay, we have two others that operate where we've had previous plant communities. So these two dominate the process of secondary succession. In the mechanism of inhibition, each species holds on to its space as long as it possibly can, fighting tooth and nail to keep its space. But some species have long lifespans and some species have short lifespans. The ones that have short lifespans turn their space over quickly, and that allows other species to colonize it. Another individual of that same species may get that space again, but you also open up that space for a longer lived species which will take over. So succession proceeds as shorter lived species die out and longer lived species kind of grab the space that they had. This is competition in the truest sense. Everybody's fighting to hold space, but because some species live and die faster than others, they turn over the space, and that leaves it open for everybody else to grab it. So shorter lived species may dominate early, but they can't hold it because they die out and longer lived species grab the space. Finally, we have tolerance. Tolerance is a mechanism in which we're not competing for space, we're competing for resources. Could be water, could be nitrogen in the soil, but the classic resource that these guys are competing for is light. So when you have plants of different growth forms, like herbs and grasses and shrubs and trees, that's going to proceed through competition for light. So early species are good colonizers, but they don't compete well for light. Late species are poor colonizers. They can't get to these opportunities very easily, but once they do, they outcompete everybody else. So this is changing the environment, this is holding space, and this is competing for resources. So let's look at the very specific situations in which each of these three things dominates succession. So first off, facilitation is the mechanism that dominates when we have new land. So here's a retreating glacier. There's no plant community under that glacier. Furthermore, this is barren rock. There's no soil here. There's no way that a tree can colonize this area. So in order for any plants to establish here, there has to be development of soil. Now that occurs as really small plants like mosses, lichens, the odd grass, maybe a few herbs, finds little niches to establish in, and they start to break down the rock into soil. When enough soil accumulates, you might get some perennial grasses and maybe some bigger herbs. And as they break down the rock further and add their decomposing bodies to the soil, then you can start to support things like shrubs. And as the shrubs further degrade this bare rock, then you have enough soil to support small trees, then big trees. Okay, and here's a volcano in Indonesia. And you can see up here, this is new lava flows. Okay, well, if there was a plant community there, it's been incinerated. So what's going on up here is virtually identical to what's going on here. Okay, no pre-existing plant community, and these areas are hostile to many plants. The only way that late successional species can possibly live there is for early successional species to alter the environment. And this is a good example of how it's not a deliberate kind of altruistic mutualism. It's an inadvertent result of early successional species getting to these areas and making a living there. They can't help it that they're breaking down the rock and adding organic matter to the little bit of soil that they're forming, and yet doing that provides opportunities for other plants that can come in and take over from them. So it's not a deliberate thing, but it is something that is inevitable in these habitats. Now, a really good question is, if we're looking at the species composition over time, how do we recognize when facilitation occurs? Well, I'm going to give you a very simple numerical example of what ecologists actually look at when they're trying to figure out, is this facilitation, is it inhibition, is it tolerance? So what we do is we look at who grabs the open space. And then we ask if space is in this state at this time, and we come back at a subsequent time, how has it changed? Is it back to open space, or has that same species managed to hang on to the space that it claimed, or has another species taken over from that first species? So I'm going to give you a very, very simple example, and we'll use a consistent example here. You're not going to have to solve any problems using these numerical examples, but I hope that they kind of illustrate what we actually look at. So here is what would typify facilitation. Okay, and let's say that we have three species. We have an early successional species, a middle successional species, and a late successional species, A, B, and C. Okay, so let's look at what the temporal pattern is of these three species. So here's open space at time t. Here's the space that species A has claimed at time t, and the space that B has claimed and C has claimed. And this is what has changed if we come back at a later date. So what you can see here is that open space is generally claimed by only one of the three species, the early successional one. And that is because the other two, the middle and late successional species, would have a very hard time living in a place that did not have soil. Okay, so these are the soil builders here. And you can always recognize facilitation in two ways. First, open space is always claimed almost exclusively by early successional species. There's very little opportunity for these guys to share that open space. There's another issue here, right? Because if we are looking at an area that doesn't have a pre-existing plant community, well, you have to disperse to get there. And we already know that early successional species are really good dispersers. They have small seeds, they have lots of seeds. Those seeds are broadcast by the wind randomly, and they get to these opportunities very easily. These guys here have progressively larger seeds and progressively fewer. So just on the basis of random chance, it's very unlikely that these guys will be able to claim lots of space. The second thing you see here is that there is an orderly changeover from one species to another. Space that was claimed by species A, they may die off because they're short-lived, and it may go back to open space. They may be able to hang on to a little bit of it. I see that I have, this adds up to 1.1 here. I've got to make one of those 0. But notice that A goes to B almost totally. A does not go to C because A has to change the environment so that B can colonize. B has to change the environment so that C colonizes. Until the middle successional species B changes the environment, the late successional species C cannot have a lot of opportunities. So when you have species A, it goes almost exclusively to species B. It takes over from species A. This changes the environment so that the next species can come in. If you look at the space that species B occupies, they may die and some of it may go back to open space. They may be able to hang on to a little bit, but look, mostly if species B is in this space, it is changing the environment so that species C can come in. So look, you get an orderly change from each state to the next one. O to A to B, B to C, and then look, C replaces itself. It's the climax community. So there are two things you look for. Number one, the early successional species grab almost all the space, open space. And number two, there's this orderly changeover from one step to the next step. One step to the next step. You don't get areas occupied by A suddenly being taken over by species C, because that's not possible. Species C requires species B to change the environment before it can come in. So it can only take over here from species B. It cannot generally take over from species A. Now notice that I didn't make the numbers exactly perfect as illustrations. And that's because I want you to remember that in dealing with a real environment, yeah, you'd see the odd oak tree getting into a little pocket of soil just randomly every now and then. So it wouldn't be perfect, and I don't want to make it look perfect. Okay, questions about facilitation. Each species is changing the environment in a way that makes room for the next species in the sequence. A to B, B to C, and then C replaces itself. Let's look at then inhibition. So inhibition is the mechanism where each species holds space. This is the mechanism that drives succession predominantly in habitats where you have most plants with the same growth form, like a prairie where everything is a grass or an herb. Nobody has a huge advantage in competing for, say, light. It's not like one grass can grow that much taller over the next grass and shade it out the way a tree could. So when you have consistent growth forms and there's not huge competition for light, then you have basically inhibition. So in this situation, each of these species that you see here is living in that space until it dies. It then opens up a little space that can be colonized by anybody. It can be recolonized by the same species, but other species can take it over. Okay, now this is a secondary successional process. So the key thing to remember here is that all of these species would be present. This is a successional process that would occur if we disturbed it. Maybe a prairie fire opened up a bunch of space. But the seeds of every one of these species is in the soil. So, open space can be claimed by anybody. So, look at the top row. Open space here can be claimed by every single species in the sequence. The only difference between these species is how long they live. This is a short-lived species, this is a medium-lived species, and this is a long-lived species. So the earliest successional species doesn't get all of the space. It shares it, maybe not quite equally, but it shares it with every other species. So everybody gets a crack at the open space in this mechanism. It's quite different from facilitation. The other thing is that notice where the big numbers are here on this diagonal. A hangs onto its space. If an area is occupied by species A, it doesn't automatically go to B because A is not changing the environment to favor B. A is hanging onto this space as tightly as it possibly can. So A to A, B to B, and C to C. The reason that the numbers increase a little bit is because this is shorter lived. It turns over its space a bit faster. This lives a little bit longer and turns over its space a little bit less frequently. This is the longest lived, and it doesn't turn over its space very much. So there's large numbers on the diagonal here, just like in facilitation, but it's a different diagonal. In facilitation, it's the A, open to A to B, and B to C, the changeover, that are the biggest numbers. Here, A stays A as long as possible. B stays B as long as possible. C stays C. So two things to look at. Where are the big numbers on the diagonal? And do each of the species get a chance at open space? If they do, it cannot be facilitation. But if only one of them gets the open space, it's facilitation. Questions? Okay, the last one then is where we have a variety of growth forms and there's intense competition for light. That's tolerance, right? So you can get a forest fire coming through, clearing out all these trees, and initially grasses and herbs come in because they have small seeds and they get to the space. Then they start competing for light with the rarer shrubs and trees that colonize initially. Also remember, this is a pre-existing community that's disturbed, so the seeds of every species are present. Once again, the open space could be shared among all the species. So we might see something like this. Now, why do I have a larger number for the early successional species than the later ones? It's because they have smaller seeds and more of them. So here, you might expect A to get most of the space, but it shares it with all the other species in the whole community. Here you see that the diagonals are shared, or the transitions are shared. So depending on whether species A is growing next to species B might shade it out and take over. Or it could be growing next to species C, the late successional one, because it has the opportunity to claim open space. So it can transition to C as well. Once again, you get an increase on this diagonal, but it's a really sharp increase. A is not a good competitor, so it dies out very quickly in competition with the others. And this diagonal grows, the numbers increase at a much faster rate than they do in inhibition. In inhibition, these numbers are much closer typically. In tolerance, these numbers are very low because they're poor competitors, and progressively increase. So this is what an ecologist would actually look at when looking at a community to see whether facilitation or inhibition or tolerance were driving succession. They look for two things. How dominant is the early successional species? If it's got virtually everything and these guys have very little to none, it's almost certainly tolerance. Certainly facilitation. The other tip-off would be that the transitions from one state to another are the highest probabilities. Open to A to B, B to C. If it's inhibition, everybody's about equally competitive. So everybody gets a share of the open space, and these numbers, A to A, B to B, C to C, they're pretty similar. This will always be the biggest one because it's the longest lived. In tolerance here, yes, all the species get a share of the open space, but the early successional species have more seeds, so they get a bit more. And the other species in the sequence can take over directly from species A here. So think about this. I'll ask you to try to recognize these patterns, but we're not going to do any calculations or anything with them. Just those two items of information. Where are the big numbers in the diagonals, if any, and who gets all the open space? That's how you tell. Okay? Any questions before we leave succession behind? Okay. Well, where's my... Yep, there we go. Okay, so we will then move on to talking about the regulation of diversity in local communities. Now, what we mean by regulation of diversity can have a couple of meanings. We can say we have a field here and it has a different number of species than a field over here. What would explain the difference in diversity between those two fields that are in basically similar environments? We could also pull way back and look at a much larger scale and say, we get a lot more species in the tropics than we do in the Arctic or the Antarctic. What would explain the differences in number of species across the face of the Earth? So first, we're going to focus on diversity in local communities. So comparing communities that are basically in the same kind of environment. Okay. So this is how we think of it. We think of basically two different kinds of regulatory things. We think of biotic interactions, and we think of abiotic regulation. Okay, in biotic interactions, predation, competition, and mutualism determine which species and how many species you can have. For abiotic regulation, it's the availability of resources, the complexity of the physical environment, or whether disturbances are opening up opportunities that regulates the number of species. Now, it's important to understand that these things can work together. They're not mutually exclusive. You can have greater niche space in one community and a different disturbance regime that produce greater diversity. We generally ask whether each of these things is important on their own because it's a very complicated thing to investigate. We're starting to get the analytical tools to ask about multiple things happening all at once, but that's really computer intensive. and we haven't made a huge amount of progress on that. So we'll deal with them one at a time. So first off, we call biotic regulation of diversity, call those equilibrium hypotheses. Now, that's a little odd because you can have equilibria down here too. Why do we use the term equilibrium? It is because if you think about the competition graph, you can get coexistence where the lines cross, right? And the point at which the lines cross is called a equilibrium. In a predator-prey system, you can get stable coexistence of predator and prey where the isoclines cross, and we call that point N. What do we call the point where the lines cross? An equilibrium, yeah. That's why we appropriate the term equilibrium and use it to talk about these biotic interactions. There can be equilibria in these abiotic things as well, but we generally talk about them as non-equilibrium because they don't come out of our Latka-Volterra models. So there are three ways to think about regulating diversity in terms of equilibrium hypotheses. One is greater niche space, one is greater niche overlap, and one is greater specialization. And all three of those things would lead to more species. So here's how to think about it. Okay, so here we have a resource axis. And here we are able to pack 5 species in. How can you get more than 5 species? Well, you could have a greater diversity of resources. So this resource axis ends here, but if we extend it, if we add a greater diversity of resources, there's more things for species to divide up. Second, you could maintain the same resource diversity, but you could have everybody overlap more. Okay, so they'd be competing more, but this is a way to pack in more species. And finally, you could still maintain the same resource diversity, but everybody could become more specialized. So this would reduce competition among them. It would reduce the size of their niches, but you could still pack more species in. So more resource diversity, more overlap, or more specialization would all three be potential ways of getting greater species diversity. What examples do we have for nature? Well, we have a number that suggest that species actually do respond to this. So here are 2 desert rat communities, and there are 6 rat species in the Sonoran Desert and 5 in the Great Basin. They're all eating seeds. The seeds have the same size range. And look, there's almost identical species diversity. And they look very much like they are undergoing a bit of character displacement in order to share those seeds. Okay, when we see patterns like this, that makes us think that, yeah, these biotic interactions can really be important. So this is an example of what makes us think that biotic regulation can be important. So what evidence do we have for any of those 3 things? Well, okay, so here's character displacement. So this would be greater specialization. We have seen a natural experiment that suggested that greater specialization influenced the number of species, and that's Darwin's finches. Right? We saw character displacement. We see this in other places too. But here's a Anolis lizard from one of the Caribbean islands, from the Bahamas actually. Okay, and this guy here coexists with 5 other species. Notice that it's got a relatively narrow niche breadth. in terms of the prey that it eats. This species here has a really wide niche, okay? And it's the only species on that island. So hey, that should look very familiar to you. This is another natural experiment that implies that specialization can be responsible for having more species in one community than another. If you have fewer species, the likelihood is that many of them will be generalists. If you have many species, the likelihood is that they will be more specialized. We see a lot of evidence like this. So we think that specialization is an important equilibrium mechanism of packing in greater diversity. What about niche space? Okay, this will take a minute to explain. So niche space, that can be hard. But what we can do is look at morphology, because morphology tells us how species make a living. And here's an example of two communities that have very different sets of morphology. Here are some bats in Canada, and the little black dots, those are the Canadian bats. Here are a whole bunch of bats from West Africa, and they're all in blue, and look at how many of them there are. West Africa has way more bats than Canada. Why is that? We can get some insight in terms of the morphology. So look, the wing shape tells you a lot about how bats work. If you have a short, wide wing, then you're really maneuverable. You can flap and you can turn on a dime. And you can catch things that fly really easily. So bats with short wings and wide wings are really good insectivores. Bats with long, flapping wings, they can fly long distances that the insectivores can't fly. They can fly from tree to tree over miles and miles and miles looking for ripe fruit. They're frugivores. So let's look at the how diverse the morphology is in Canada. Well, what you see is that the wing size here is really compressed. All of these bats make their living in almost exactly the same way. In Canada, they're all insectivores. They all have the same wing shape, and they all eat insects. In West Africa, you have some bats that fly really long distances. You have some that fly short distances, have long wings, short wings. And these guys have many, many, many more ways of making a living. So the diversity of morphology maps the diversity of ways of making a living. There's more niche space to divide in Africa than there is in Canada. Basically, you don't have a lot of tropical fruits in Canada. You do in Africa. All you've got for bats to eat in Canada is insects. And sure enough, that's what they all eat. But there's only so many ways to divide up the insects. So you have fewer species. So this is a great example of a way of getting at how much niche space there is for a species to divide up. Now, what about the third one, greater overlap? What do we know about the evolutionary response to competition? What do we call it? Shindy, what do we call it when two species compete over time? They coexist and they overlap, and then what happens over time? Less overlap. We know that evolution does not like niche overlap. We know that fitness is lower where you have niche overlap. Niche overlap is not something that we see very commonly, and that makes total sense. When two communities differ in terms of species diversity, it's usually because there are more specialists in one community than another, so more species, or because there are more ways to make a living in one community than another, more niche space. But niche overlap, that's unstable.
So, what does the desert rat example fall under?
The desert rat example falls under character displacement.
That's not one of the three main. It wasn't one of the three main.
Well, okay, that is greater specialization. Okay. All right, so we will come back and talk about the non-equilibrium hypotheses next time. Please email me and let me know whether you're in or out on a presentation. If people are abandoning presentations left and right, then we'll reorganize and I'll ask you what you'd like to do. Okay? What? Email me. You have to email me. This is not acceptable. You must email me.